The majority of power electronic circuits are nowadays built on insulated-gate field effect transistors. In fact, in digital, and just as much in power devices, field effect transistors are used more often than their bipolar counterparts. First of all, field effect transistors are easier to control. The control in such devices is insulated from the current transport zone, so no power is required to maintain in it the on state. As soon as the field effect transistor is on, its control current is virtually equal to zero. Besides, the charge required for switching is significantly lower, and therefore so is the time of the charge transfer. These features help to substantially decrease the issue of excessive voltage drop on the device in the static mode, which is inversely proportional to excessive control charge and dramatically decreases the power-off time of the transistor. That is why it is much more beneficial to use field effect transistors due to the simplicity and efficiency of control circuits. Another important factor for power electronics is the fact that the field effect transistor channel acts as a resistor, so the voltage drop between the source and the drain changes linearly to the current flowing through the channel. This linear relationship is described by on-state channel resistance according to RDS terminology and remains constant at a given switch voltage and chip temperature. As opposed to the PN junction, with a negative temperature coefficient of 2.2 mV, the on-state channel resistance of field effect transistor is characterized by positive temperature coefficient equal to 0.7%, C1%. This enables simple parallel connection in power devices, when the use of single components is not feasible or generally impossible. Due to the positive temperature coefficient that works as slow negative feedback, currents are automatically rectified through individual switches. This leads to a balance when the current flowing through all the transistors connected in series is identical in value. The initial difference in open switch voltage and various thermal resistance values can lead to a substantial current distribution difference of up to 30%. The power switches available in the market from various world manufacturers can be divided into three types. Power field effect transistors with double diffusion using a gate structure based on multicrystalline silicon. Trench, a technology based using V-shaped trenches with increased cell density of power field effect transistors. And finally, lateral field effect transistors. Lateral field effect transistors have much lower capacitive parasitics, which is why their switching speed is higher and they do not require powerful control circuits.